Hello, welcome back. In the last class, we were looking at some examples related to constraint optimization problems, and we were checking the conditions about the optimality. In particular, we were looking at first order Kkt conditions. So, this was the example that we were looking at. So, minimize x1 minus 9 by 4 square plus x2 minus 2 square and subject to these constraints, and you have a non-negative constraints on x1 and x2. And we saw that the constraint set is a convex set, the objective function is a convex function. So, this is a convex programming problem. Further, there exists at least one point in the interior. So, the Slater's constraint qualification holds, and it is enough for us to find out a Kkt point which satisfies first order conditions, because under the convexity these first order Kkt conditions are necessary and sufficient. So, so the constraint set is shown here by the shaded region, and this was the problem that we want to solve. So, we checked that this 0.24 does not satisfy the Kkt conditions, and that is mainly because the Lagrangian multipliers corresponding to the second constraint, second inequality constraint, become negative, and therefore, this point cannot be a this point cannot be a Kkt point. So, now let us assume that the first constraint x square minus x2 less than or equal to 0 is active. So, this is the first constraint, and suppose that that is active. Now, let us consider that case. So, let us assume that let us consider the part B where constraint 1 is active. And since constraint 1 is active, the rest of the constraints are inactive. So, therefore, at optimality what we expect is that the Lagrangian multipliers corresponding to the remaining constraints are all 0. So, lambda 2 star equal to lambda 3 star equal to lambda 4 star equal to 0. Now, let us consider a point at x star to be 3 by 2 and 9 by 4. At this point, let us see what happens. So, gradient of L x with respect to x star lambda star equal to 0. So, if we look at the gradient, so if you look at the Lagrangian which is given here, and if we take the gradient of that with respect to x and evaluate it at the given point x star, and we know that lambda 2 star, lambda 3 star and lambda 4 star equal to 0. So, our aim is to get lambda 1 star, and that is what we will do now. So, this implies minus 3 by 2 plus 3 lambda 1 and half minus lambda 1 is equal to 0. So, we have substituted this value of x star and lambda star. So, we just have equations in terms of lambda 1, and this implies lambda 1 star to be half, and that is greater than 0. So, this does satisfy our requirements. So, therefore, this point x star equal to 3 by 2 and 9 by 4 and lambda star equal to half 0 0 0. So, x star lambda star is a Kkt point. because it satisfies all our requirements, and therefore, the first order necessary conditions are satisfied, and this being a convex programming problem, these conditions are also sufficient as the Slater's constraint qualification holds. Now, let us consider the problem. So, as we saw that x star equal to 3 by 2 9 by 4 is a strict local minimum of this problem. Now, suppose we replace this the first inequality constraint by the following inequality constraint, that x1 square minus x2 whole cube is less than or equal to 0. So, the other constraints remain the same, only the representation of the first constraint changes. Now, if we look at the only change that is made is in the representation of this constraint, and so this constraint is changed to x1 square minus x2 cube less than or equal to 0. And now, if we look at the point 3 by 2 9 4, so let us see what happens. So, let us look at the third case. So, suppose the first constraint is x1 square minus x2 whole cube less than or equal to 0. Now, let us look at x star, which is the local minimum of this problem, which is 3 by 2 and 9 by 4 at x star. You will see that gradient h1 x star is equal to 0. And therefore, so if you represent this constraint like this, then this point is not a regular point, because this is the only constraint which is active at this, and it is not a linearly independent set. So, this is not a regular point. So, although the constraint set remains the same, the representation of the constraint is very important, and this example is just to illustrate that fact that if we change the representation, a local minimum may not be a regular point. So, this is a very important point that one needs to understand. Okay. Now, let us look at another example. So, you will see that this point which was a local minimum, strict local minimum, was not regular. So, we really cannot apply the Kkt conditions. Now, let us look at another example. So, here the problem is the following. We want to find a point on the parabola. The equation of the parabola is x2 equal to 1 by 5 x1 minus 1 square, and that point should be closest to the point 1 comma 2 in the Euclidean norm sense. So, we are interested in finding a point on the parabola which is closest to this, or since this is a problem in 2-dimensional space, one can think of the interpretation of this problem as we want to find a circle of minimum radius centered at the point 1 comma 2. So, we want to find a circle centered at 1 comma 2 which has the minimum radius and which touches the parabola. So, let us write down the problem formulation. So, we have x1 and x2 as the two axes, and so this parabola, so the given point is 1 comma 2, So, what we are interested in is finding out the circle of minimum radius which touches the parabola. So, the objective function is to minimize x 1 minus 1 square plus x 2 minus 2 square, and then that point should touch the parabola. So, the equation of the parabola is x 1 minus 1 square is equal to 5 x 2. So, the parabola would look, so it will touch the x 1 axis at 1 0, and the parabola would be something like this, and the point 1 comma 2 is a point somewhere here. So, this is the point 1 comma 2. So, we want to find out the circle of minimum radius which touches this parabola. So, note that there is only one equality constraint. So, let us write down the Lagrangian first, and the Lagrangian is the objective function which is x 1 minus 1 square plus x 2 minus 2 square plus mu into the constraint E of x equal to 0. So, mu into x 1 minus 1 square minus 5 x 2. So, let us write down the gradient of the Lagrangian with respect to x, and that gradient is nothing but 2 into x 1 minus 1 plus 2 mu into x 1 minus 1 and 2 into x 2 minus 2 minus 5 mu. So, this is the gradient of the Lagrangian, and we can write down the Hessian of the Lagrangian with respect to x. Note that this Lagrangian is a function of x as well as mu, but just to avoid notational clutter, we are not writing the dependence of L on x 1, x 2 and mu, but we assume that L is dependent on all these parameters. So, the Hessian of this Lagrangian will be 2 plus 2 mu, then the derivative of this term with respect to x 2 is 0, and the derivative of this term with respect to x 2 is 2. So, this is going to be the Hessian of the Lagrangian. Now, let us check when does the Lagrangian becomes 0. So, this implies that, so if we look at, so we have to equate these two quantities to 0. So, this quantity is nothing but x 1 minus 1 into 2 plus 2 mu, that should be equal to 0, and 2 into x 2 minus 2 minus 5 mu should be 0. So, let us write down those quantities. So, x 1 minus 1 into mu plus 1 equal to 0 and 2 x 2 minus 2 minus 5 mu equal to 0. Now, if you look at the first equation, so we will have either x 1 equal to 1 or mu equal to minus 1, and note that this mu is the Lagrangian multiplier corresponding to the equality constraint. So, it can be negative. So, let us consider the first case where we say x 1 star equal to 1, because then this first equation is satisfied. Now, once we know x 1 star, we have to get x 2 star, and how do we get x 2 star? So, we look at the constraint. So, when x 1 star equal to 1, we need to satisfy the equality constraint, and therefore, x 2 star will be 0. So, x2 star will be equal to 0, and if we plug in that value here, what we get is mu star to be minus 4 by 5. So, we get a Kkt point where x1 star equal to 1, x2 star equal to 0 and mu star equal to minus 4 by 5. Now let us look at the second order sufficiency conditions. So, for that purpose we will need gradient Ex star. Now, this Ex star is basically this constraint. So, we can write this constraint as Ex star Ex equal to 0. So, x1 minus 1 square minus 5x2 equal to 0. So, this is our equality constraint. So, gradient Ex star will be 2 into x1 minus 1 and minus 5 evaluated at x equal to x star. So, let us evaluate it at this point 1 comma 0 and it will be 0 comma minus 5. So, let us define the set S to be the set of all D's not equal to 0 such that gradient Ex star transpose D equal to 0. And this set is nothing but set of all D's not equal to 0 such that gradient Ex star is 0 comma minus 5. So, 0 into D1 minus 5 D2 is equal to 0. And this so therefore, S becomes the set of all these not equal to 0 into D1 minus 5 D2 equal to 0, which is what we saw earlier, and this is nothing but. So, you will see that in order that this equation is satisfied, D2 has to be 0, while D1 can take any value. So, D1 belongs to R and D2 should be 0. So, what we have is the set of all points D1 comma 0 such that D1 belongs to R and we do not want D to be a 0 direction. So, D1 not equal to 0. So, this is our set S. So, our aim is to get a vector from this space, any vector from this space, and see whether with respect to this the Hessian matrix is positive definite. So, let us take a vector D1 0 from this space. Now, the Hessian matrix evaluated at mu star equal to minus 4 by 5 is 2 by 5 0 0 2 into D1 0. So, this is D transpose Hessian of L into D, where D belongs to the space of vectors which satisfy that gradient Ex star transpose D equal to 0. So, this quantity is nothing but 2 by 5 D1 square. Now, D1 is a real number, non-zero real number, and therefore, 2 by 5 D1 square is greater than 0, and therefore, the point that we saw here is a Kkt point and is a strict local minimum. So, this point is a strict local minimum. Now, let us look at another case. So, if you recall that we consider the case where x1 was set to 1 and this equation was satisfied. Now, let us consider the case where mu is set to -1. So, we have now case 2 where mu star is equal to -1. Now, if mu star is equal to -1 and if we substitute that here, so what we get is x2 star to be also -1. So, we get x2 star equal to -1, and if we look at the constraint set, so x2 star is never -1, it is always non-negative. So, x2 star equal to -1, this is not a feasible point. And therefore, we cannot continue this case further, and therefore, you will see that this point 1 0 is a strict local minimum, and if you look at the figure, so this point is a strict local minimum. Now let us consider this problem again. So, we have minimize x1 minus 1 square plus x2 minus 2 square subject to x1 minus 1 square is equal to 5x2. Now, if we look at the constraint and the objective function, one will be tempted to make the substitution for x1 minus 1 square, because x1 minus 1 square is equal to 5x2, and one will be tempted to use that equality in the objective function. So, let us see the reformulation of this problem. So, minimize 5x2 plus x2 minus 2 square, and this is the problem with respect to x2. So, this is the common mistake which is made while reformulation, is that we simply substitute x1 minus 1 square to be 5x2 and solve it as a unconstrained problem. But this is not correct, because if you look at this constraint, we have not fully utilized this constraint in the objective function. Note that this x1 minus 1 whole square is a non-negative quantity, and therefore, we cannot have this constraint, but rather we should write the constraint minimize subject to the constraint that x2 greater than or equal to 0. So, this is going to be the correct reformulation of the original problem. So, the original problem was constraint, and we now have another constraint problem which is an equivalent problem. Now, interestingly, this problem can be converted to an unconstrained problem. So, suppose we define y square to be x2. So, y square is a non-negative quantity, and therefore, it always satisfies y square greater than or equal to 0, and then we can substitute this y square in this objective function, and what we get is the following problem, where we minimize phi u y square plus y square minus 2 whole square, and then we can say that y belongs to R. Now, this problem is an unconstrained problem. So, while reformulating a given constraint problem, one has to be extremely careful, and this problem we can solve it using our earlier optimality conditions, the first order and the second order optimality conditions for unconstrained optimization problems. So, we take the derivative of this and equate it to 0, and that will give us the solution. You can check that that gives us y star to be 0, and therefore, x star x 2 star equal to 0 and x 2 star equal to 0, which means that x 1 star is equal to 1. So, by converting appropriately into an unconstrained problem, we got the same solution for the given problem 1, 0. So, it is very important to understand that reformulation has to be done in a careful way. So, we formulated the problem like this, and we saw that 1 0 is a Kkt point with mu star to be minus 4 by 5, and it also satisfies the second order conditions with respect to the Hessian matrix, and therefore, this 1 0 is a strict local minimum, and reformulation has to be done in a careful way. Now, let us look at an unbounded problem which is given here. So, minimize minus 0.2 into x 1 minus 3 square plus x 2 square subject to the constraint that x 1 square plus x 2 square greater than or equal to 1. Now, this quantity is a non-negative quantity, this quantity is also a non-negative quantity, but this quantity is multiplied by a negative quantity. So, if we make x 1 very, very large, then that quantity will be multiplied by a negative quantity, and therefore, truly the minimum does not exist for this problem. But does this local minimum exist, and that is what we want to answer. So, as I said that the objective function is unbounded, and let us find out whether this point 1 0 is a strict local minimum or not. So, the problem that we want to solve is minimize minus 0.2 into x 1 minus 3 square plus x 2 square subject to minus x 1 square minus x 2 square plus 1 less than or equal to 0. So, the constraint was x 1 square plus x 2 square greater than or equal to 1. We just wrote it in the form h x less than or equal to 0. Now, if we draw the constraint set, so we have the two axes x 1 and x 2, and suppose that this is the circle whose equation is x 1 square plus x 2 square equal to 1. Then what we are interested in is the region where x 1 square plus x 2 square is greater than or equal to 1. So, that means we are interested in the region on the circle or outside the circle. So, we are interested in this feasible set, and clearly the objective function is unbounded and therefore, the minimum does not exist, but let us see whether there is a local minimum at this point at 1 comma 0. Now, let us write down the Lagrangian as is our usual procedure. So, Lagrangian is minus 0.2 into x1 minus 3 square plus x2 square plus lambda into minus x1 square minus x2 square plus 1. So, lambda is the Lagrangian multiplier corresponding to the inequality constraint, and clearly this lambda has to be non-negative. Now, if you take the gradient of L with respect to x, and that will be minus 0.4 into x1 minus 3 minus 2 lambda x1 and 2 x2 and minus 2 lambda x2. This is the gradient vector, and the Hessian matrix will be minus 0.4 minus 2 lambda, then the derivative of this with respect to x2 is 0, and the derivative of this with respect to x2 is 2 minus 2 lambda. So, this is going to be the Hessian matrix, and we are in particular interested in finding out whether the point 1 0, this point is a strict local minimum or not. So, at x star to be 1 0, if we equate the the gradient of the Lagrangian to 0, which implies, so what we have is we substitute x1 equal to 1 and x2 equal to 0 in this the gradient of the Lagrangian, and what we get is 0.8 minus 2 lambda and 0 equal to 0, and this implies lambda star to be 0.4. So, this quantity is greater than 0. So, the point x star lambda star is a Kkt point. Now, so therefore, x star lambda star is a Kkt point. Now, we have to see whether it satisfies the second order condition, and for that purpose what we need is the derivative of the gradient of the constraint. So, this is our constraint, and we will write it as hx equal to 0. So, the gradient hx is nothing but minus 2 x1 minus 2 x2, and that we evaluate it at 1 0. So, gradient hx star will be minus 2 x1 minus 2 x2, and x1 is 1 and x2 is 0. So, it will be minus 2 0. Now, let us write down the set S. S is, since the only constraint that is active is x1 square plus x2 square equal to 1. So, let us write down the set D to be the set of all non-zero directions such that gradient hx star transpose D equal to 0, and that is nothing but the set of all D's non-zero such that minus 2 D1 plus 0 into D2 equal to 0, and this is nothing but the set of, so this implies that D1 has to be 0, D2 can be any value. So, set of all 0 comma D2 such that D2 belong to R d2 not equal to 0. So, let us take a vector from this space. So, let us take a vector 0 d2 itself and then see whether the Hessian is positive definite or not. So, the Hessian evaluated at this x star lambda star will be this multiplied by 0 d2. So, d transpose Hessian of the Lagrangian into d, where d comes from the space S, space spanned by the set S. Now, note that this is a one dimensional space. So, it is enough to take only one vector here, and this is nothing but 1.2 d2 square, and since d2 is not 0, this quantity is greater than 0, and therefore, so therefore 1 0 is a strict local minimum. So, although the function is unbounded, this point is a strict local minimum of the given problem. Now, let us take this example and solve it with respect to the equality constraints which are shown here. The problem is to minimize x1 square so subject to minus x1 plus x3 equal to 1 and x1 square So, note that we have two equality constraints here and both have to be active at a optimal point. So, let us write down the Lagrangian to be the function. So, for the first constraint, let us assume that the Lagrangian multiplier is mu 1 and for the second constraint Lagrangian multiplier is mu 2. So, we have minus x1 plus x3 minus 1 plus mu 2 into x1 square plus x2 square minus 2x1 minus 1. Now, let us write down the Lagrangian, the gradient of the Lagrangian to be. So, you will see that the gradient of the Lagrangian is 2x1 minus mu 1 plus 2 mu 2 x2 I am sorry 2 mu 2 x1 minus 2 mu 2. Then the second component is with respect to x2 and that is 2 x2 plus 2 mu 2 into x2. And the third component is with respect to x3 and that is half x3 plus mu 1 . Now, the Hessian of the Lagrangian will be a 3 by 3 matrix and that will be, so we have 2 plus 2 mu 2 and there are no terms in this which involve x2 and x3. So, the other components are 0 and since it is a symmetric matrix, these components are also 0. Now, let us look at the second term. So, the derivative with respect to x2 is 2 plus mu 2 So, we have 2 plus 2 mu 2 and there is no term involving x 3. So, in the second component, and in the third component we have half. So, this is going to be the Hessian matrix of the Lagrangian. So, what we need to do is that we need to find out x such that the gradient of the Lagrangian vanishes and the two constraints are satisfied, because those are equality constraints. So, they need to be satisfied. So, the other equality constraint is x 1 square plus x 2 square minus 2 x 1 equal to 1. So, in all we have 5 variables x 1, x 2, x 3 and then mu 1 and mu 2, and we have 5 equations. So, we have 5 equations and 5 unknowns. So, we have 5 equations in 5 variables, and you can check that one solution of this is x star to be 0 0 1 and mu star to be minus half and 1/4. So, both the constraints are active at this point, and one can write down the Kkt conditions for this. And the other point is, so you can find out the other x star and the other mu star, and write down the conditions and check the Kkt points for this. Okay. So, so far we have seen the constraint optimization problems. So, in particular we were looking at the problems of the type minimize f x subject to h j x less than or equal to 0, j going from 1 to L, and E I x equal to 0, I going from 1 to M. Now, we also wrote down the Kkt conditions for this problem. In particular, we saw that the gradient of the Lagrangian vanishes. So, gradient f x star. So, there exists x star, lambda star, mu star, such that gradient f x star plus sigma j lambda j star gradient h j x star plus, so j going from 1 to L plus sigma I going from 1 to M mu I star gradient E I x star to be 0. And we have the complementary slackness condition, which is lambda j star h j x star to be 0 and lambda j star non-negative. So, the Lagrangian multipliers corresponding to the inequality constraints are non-negative, the Lagrangian multipliers corresponding to the equality constraints are unrestricted in sign. So, we are interested in finding out x star, lambda star and mu star which satisfy this, and then if the second order conditions are satisfied at this x star, lambda star, mu star, then we say that x star is a local minimum. So, let us assume that x star be a local minimum. So, our aim is to solve this problem and get x star which satisfies these conditions as well as the second order conditions. Now, to satisfy these conditions, what we need is that we need x star, lambda star and mu star. Now, suppose if we have some problem for which lambda star and mu star is a solution, or in other words, suppose we have some problem, as of now we do not know the nature of that problem. So, a nonlinear programming problem, NLP in lambda and mu. Okay. And let us assume that this optimization problem has a solution lambda star and mu star. So, let lambda star which is greater than or equal to 0 and mu star be a solution of this problem. Now, suppose that this problem is easy to solve, then what one can do is that one can get lambda star and mu star from this, and suppose it turns out that that lambda star and mu star can be used here, and then we can easily get a solution of this problem. So, given a problem, the idea is that if we can find out another nonlinear programming problem involving variables lambda and mu, where lambdas are non-negative, mu's are unrestricted in sign, and they have the same dimension as the number of constraints in the original problem, like lambda will have lambda will be L dimensional and mu will be M dimensional, but lambdas are non-negative. So, if we have such a problem and if we can get a solution of this problem very easily, and if that solution can be used to solve this sets of equations to find x star, then we directly get the solution of this problem. So, this problem which we are going to study, this problem is called a dual problem, and the problem which we had originally written, this is called the primal problem. Now, note that although for a primal problem there exists a dual problem, but a solution of the dual problem does not always give us the solution of the primal problem. Only under certain conditions the solutions of this dual problem, which are lambda star mu star, they can be used to get a solution of the primal problem. So, this is called the duality theory, and in the next lecture we are going to see that under what conditions do the primal and the dual problems have the same solution. And the advantage of dual problem is that many times this problems are easier to solve, and therefore, and they also have some nice structure, and one can utilize that nice structure of dual problems and finally get back the solution of the primal problem. So, we are going to see those duality related ideas in the next class. Thank you.